Oh, one little dilemma I have is that I just realized not too long ago because I have two classes on Monday Wednesdays. I have Math 285 at 9:30 and then this, and I record them both. And I realized not too long ago that I'd forgotten to upload this morning's class, um, which is what you see happening now. Looks like it'll be done soon. And the problem is, this Mac has only flash storage, 128 gig total, um, and I don't have a lot of disk space, so this file is hogging some of that, and the video of class I'm recording now is hogging it too. So hopefully, between the two of them, they will not chew it all up and cause severe problems. So I'm keeping an eye on this so that when these 8 minutes are up and this video is completely uploaded to YouTube, I will immediately delete it. So we'll see how this goes, and hope for no disruptions. Okay, at least a screen recording doesn't take as much space as like whenever class I'm at the board and recording myself doing that, and that takes up more. I also made quite a bonehead mistake in that class, so hopefully this will go better. All right. Now, if you look at the schedule, for the next section, 3.2, I have 3 full class periods budgeted for it. That's quite a bit of time, but it's also that much of a pain of a section. But I see no reason why I can't take some time to see if anybody has any homework questions right now from 3.1. Nope. It's all going swimmingly. You gotta give out a bunch of hundreds.
Yep.
Okay. Okay. Yes.
So that first one, where you accept the function, because apparently I didn't do the question very carefully.
Oh, which question?
Diagonal, solve the system diagonal.
Yeah, write a script to solve.
It's a specific matrix, so enter a function for it.
Oh, yeah, I don't care. Yeah, yeah. I figure a script would involve very slightly less than a function, but if you want to write a function, fine with me. Okay, so okay. Well, that was also me stalling for time a little bit because I want this dang upload situation to be over with. Okay, 6 minutes left. Okay. Yes.
In the last class, it seems like you're going to explain something with exploration 329
Oh, right.
and time again.
Okay, yeah, and I had deliberately given away what the code was for that. So, although, okay. Okay, and then the other part of the question is actually to try it on a specific matrix. So what's your question about that?
You were trying to use that to explain, I think, flux.
Oh,
You do that in Matrices.
okay.
So I thought you were going to explain something.
Oh, no, the only reason I stepped through that writing that function was just an example of how to write MATLAB functions to perform these kind of manipulations, working with matrices and so forth. That example did not have anything to do with flop counting. So I was using the Gaussian elimination algorithm for that. Okay, so.
Do we still go ahead and do this homework now?
Well, now I've put out the code for it. So, okay. Well, I mean, so I still want to do the other part of the question. Yeah.
Could you repeat that? Or your answer to his question? I'm sorry.
Oh, okay. So exploration 329. Even though I gave away the code, I still wanted to include it in the submission, just because I give a specific matrix to, yeah.
So next time, we don't have to do it and turn it in this homework, okay?
Oh, no, it's part of the next one, yeah. Okay. Yeah, because the funny thing is, section 3.1 has the algorithms for Gaussian elimination and back substitution for you to implement as part of the 3.1 homework. I don't really discuss forward substitution, and I was going to use that as an example since it's not in that section, but then I forgot, oh wait, it's in the next section. So, oh well. There's your one and only freebie. The last time I taught this class was 2 years ago. I found myself almost routinely giving away the answers to homework problems because I'd forgotten if I had assigned them. And I'm a lot better about that now, yes.
That means you can go back to your website
Oh.
and.
And I don't think... I give away, like... Oh, that's right, you can watch the video. If you're going to go to that much trouble, you might as well just do the problem legitimately. Yes.
I was playing with that try L and try U functions.
Yeah.
That second parameter with the -1.
Yeah.
They both take away zeros from the diagonal, or like from the same direction. I mean.
Oh, I mean, try L versus try U. Well, so yeah. So let's do some examples there. Okay. Oops. Need to make this a lot bigger. Okay. Okay. So I'll just make a 4x4 matrix there. So for example, if I do try L, a -1. So what that does is it will retain all elements of a matrix starting from so main diagonal is number 0. This one right above it is also called a super diagonal. That's diagonal number 1, number 2, number 3. And then the ones below the diagonal, like this right here, is often called the subdiagonal. So it's the first one, that's diagonal number -1, -2, -3. So try L will retain. So if I just do try L, whoops, I was accidentally using a Python comment character in MATLAB. This is what you get for knowing more than one language. Okay, programming language. So default usage. Okay, so try L A with one argument just takes everything that's on or below the main diagonal and retains that, zeros everything else. Whereas if I specify a second argument, it will keep so whatever I specify, it'll keep everything from that diagonal on down. Whereas if I do try U of A, again, the simplest usage keeps the upper triangle. So if I specify the same second argument of -1, it will take everything from that diagonal and above and keep it. So these are nice for constructing examples involving triangular, upper or lower triangular matrices. And I should mention, if I go back to try L, so this zeroes out the main diagonal also. This is what is called a strictly lower triangular matrix that has only a triangle below the diagonal, nothing else. Okay, so I don't know if that answers your question or.
Yeah, I was just playing with something. I think I didn't make it in by matrix, so it might have just been linear.
Oh, okay. Oh, yeah, that would be a problem. Yeah.
I was just playing around with functions.
Oh, okay. Okay. Other questions? All right. The upload is finished. Cool. So now I will delete the file from this morning's class. Okay, yeah, 19 gig. It's all I have available. And so we have a video from this morning's class took like 5 gig, or 5 or 6. Okay, so crisis averted. Okay, now, so the thing is, everything we've seen up to this point of doing Gaussian elimination, if we were to do it on paper, so far would not be any different than what you would have done like in a typical first course in linear algebra, like our Math 326. But starting right now is where we deviate from what's done in classes like that. Okay. Now, so first to set the stage for why I'm going to show you what I have, what I'm about to today. So a current procedure for solving ax equals b, as it was described in the previous section. Okay. So first, so this is like you would in linear algebra class. So first you form the augmented matrix. That you get by taking A and B, and so adding B onto A as an extra column. And then use row operations, and this is Gaussian elimination, to reduce the augmented matrix to upper triangular form. In those classes, it's referred to as row echelon form. Okay. So adding multiple of one row to another, and if necessary, row interchanges. That's something I'll talk more about later in this section. And then finally, use back substitution. On U, so the upper triangular form, U is what's obtained from those row operations, and the modified right-hand side, since row operations are being applied to both A and B by the Gaussian elimination algorithm that I showed you in the last section, and then you're done. Now, the thing I want to point out, though, is the choice of row operations formed on both A and B are determined solely by A. So the problem is ideally we should be able to reuse information if solving another system that has the same matrix but a different right-hand side. So, but the thing is, we worked on both A and B. So what's necessary is, to do this, we need a record of row operations performed on A to use later with a new B. So, in other words, if you're solving many systems of linear equations that have all have the same matrix, but they have different right-hand sides, you don't want to perform Gaussian elimination all over again. You want to do that once on A. Because keep in mind, Gaussian elimination on A, and so in other words, I'm specifically excluding B, is by far the most expensive part. Should only have to perform once. Because it doesn't depend on B at all. Okay. It's kind of funny when I'm in the middle of class and I see someone submits a quiz. So. Happens a lot, though. Okay. But the procedure of Gaussian elimination, as I've described it, is not really conducive to that, because you need to be able to take those same row operations and have some concise description of them to be able to apply to a B that you might get at another time. So we don't really have any... we need some kind of storage of that sequence of row operations. Okay. So what we'll do is we will examine elimination without involving B at all. Okay. Now, before I go into that, the task, so this is useful if solving, as I mentioned earlier, I want to get in writing here, many systems with same A, different B. Now you might be thinking, am I just making this situation up? Does this actually happen in nature? That someone really does have a need in a practical application to solve many, many systems with same matrix with different right-hand sides? Yes, I'm not actually making this up as some toy situation just to justify some funky mathematics. And yes, some mathematicians probably will do that, but I don't. I like to have at least some purpose. Although, actually, no, I'm not above doing that, but I do want to keep it relevant for you guys. So when this happens, and I don't want to get into too much into the details here, but it's something that we will see later in the semester. So using an implicit time-stepping method to solve a system of a linear system of ODEs with a time-independent Jacobian matrix. So in other words, y prime. Dang it. Y prime is equal to J Y. Okay, so there's something system of this form where J is the Jacobian. So for that would lead to a system Ax equals B, where the matrix itself is not changing from time step to time step. The right-hand side, the B, is always changing. It's the solution from one time to the next. So it's exactly the situation that I'm describing. So it'd be nice to just do Gaussian elimination on J once and be able to reuse that information for all the time steps that happen. Now, this topic of implicit time stepping, etc., will be seen in Chapter 12 that we'll get to closer to the end of the semester. So let's bring this up so you know that there actually is a need for this. Okay. All right. And it's going to lead to what is called the LU decomposition. So first we're going to scrutinize this Gaussian elimination process. So row operations that we have is so scaling rows, interchanging rows, and finally subtracting a multiple of one row from another. Okay. Whoops. Okay. So all of these can be described by multiplying A on the left by what is called elementary row. Okay, so these are called elementary row operations. Because mathematicians always like to either name things or talk about things in a way that makes them seem like they're really easy. How many times pick up a math book and the author says, it follows at once that, or clearly, blah, blah, blah. So I have to confess that I'm guilty of that too. Okay, so I'll give some examples here. All right. So interchanging rows 1 and 3. Okay. And I just realized I'm maybe doing something that takes a long time for me to type out, but probably not too much different than writing it on the board, though. Okay. Well, at least in this setting, I can copy and paste. Okay. So I'm just going to make up a matrix here. Okay. Okay. All right. Actually gonna. All right. Wait. Where'd my matrix go? Okay. Now I'm gonna multiply the matrix A on the left by matrix E that will have the effect of swapping rows 1 and 3. So what that matrix will look like is, well, first I'm going to type out the identity matrix. But then I get a mess of it, so don't copy this down. Well, probably don't need to take notes anyway. Okay, so what I will do, and really the elementary row matrix, what you do is you take the identity matrix that I've typed out here, and you perform a row operation on it. So I'm going to swap the first and third rows of this matrix. Okay, so this is identity with rows 1 and 3 swapped. So taking this matrix that I've made up and multiplying it on the left by this elementary row matrix will have a desired effect of swapping rows 1 and 3 in that matrix. Okay. Okay. All right, so this would be the product. All right. Now, so that's one type of row operation. But then a more interesting row operation for us would be subtracting multiple of one row for another. So subtracting 2 times row 4 from row, wait, something went wrong here. Okay, from row, sorry, 2 times row 1 from row 4. Okay, so all right. I'm just going to be with some mass copy pasting going here. Okay. All right, so first what I'm going to do is I'm going to restore the identity matrix. Okay. So what I'm going to do is I want to take 2 times row 1, so 2, 0, 0, 0, and subtract it from row 4. So that's going to cause a -2 to appear in this position. So that gives an indication of a row operation that's being performed, that because it's in row 4, that's a row that's being worked on. Because this entry is in the first column, that's the row that's being multiplied by something to subtract from this row. So what will happen is, okay. And notice the first 3 rows of this matrix are the rows of identity. So the first 3 rows of this matrix will not be affected. So what I'll do is, so take twice this row and subtract it from this row. So 1 minus 2 is -1. 0 minus 4. So -6 minus a -2. And then 8 minus 8 minus 6 will be, thank you, will be 2. All right, so that's a result of performing that row operation, this row operation on this matrix. So in other words, we have a simple way of describing each individual row operation. So if we can easily describe each individual row operation, can we efficiently, and in terms of time and space, so in other words, computation time and storage space and memory represent all of the operations needed to carry out Gaussian elimination. Okay. Now, the thing I want to point out about, now, I'm not going to really deal with okay. So I'm not going to deal with row interchanges right now. That's something I'll focus more on next week. But okay. So I'll focus on this kind of operation here, subtracting a multiple of one row from another. So note that the second matrix E, for subtracting a multiple of one row from another, is what's called a unit lower triangular matrix. So what does that mean? Is lower triangular, so all entries above the main diagonal are 0, and all diagonal entries are equal to 1. So that's where the unit part comes into play. Okay. Now, the other thing I want to point out is lower triangular instead of upper, because it adds a multiple of row J, or subtracts a multiple of row J from row I, where I is greater than J. Okay. And Gaussian elimination always does that. You're trying to zero entries within a particular column, column J, that sit below the diagonal. So it's always performing set row operations of that type. It's always going to be lower triangular. If I had been less than J, then we'd have a unit upper triangular matrix. Okay. Now, I'm going to point out properties of unit lower triangular matrices. That'll be very helpful to us. All right, so first, the product of two unit lower triangular matrices is unit lower triangular. Now, the reason why I put the word unit in parentheses in both cases is because I could drop that from a sentence and it's still true. So multiplying two matrices of the same triangularity always preserves that triangularity, lower or upper. If they both happen to be unit, then that aspect is also preserved. I won't go to trouble of proving it. It's something that you could very laboriously try to prove yourself. I don't believe I assigned that for homework, but if I did, sorry. What?
You did.
Whoops. Okay. Okay. All right. It's more tedious and hard. I'll put it that way. Because you're doing all this subscripting and stuff. Okay. Well, really what you'd be doing is, under the assumption that any entry above a diagonal in both matrices must be 0, that the same must be true in the product. So you want to show, like, if you have aij in the product where I is strictly less than j, it's got to be 0. And similarly showing that if aii in the product must be 1. Okay. So I'll make the comment for this. So it can be proven using the general formula for matrix multiplication. I have a section on that, and so I have two appendices in the book. Appendix A is a review of calculus. Appendix B is a review of linear algebra. So all the essentials are there. Okay, and note that for an upper triangular or lower triangular matrix L, ij is equal to 0 if I is strictly less than j. So that's the kind of property of lower triangular matrices to use. So that's how you take advantage of a knowledge that it is lower triangular, or trying to prove that something is lower triangular. Right. So hopefully those hints make it somewhat bearable. I think actually one thing I want to check on. Speaking of hints. Okay. Oh, I do have it. Ah, yes. Okay. I have homework hints that I wrote up from 2 years ago. They're not. I think they're not posted at this time. No, they're not, because I needed to update them for this year. I will post them. Yes.
I do have one question about stuff that's posted. The notes for January the 27th.
Oh, wait a minute. Sorry, where?
The notes for the 27th.
Okay.
Class. I just was going to wonder if you.
Oh, it's actually the same document from the 22nd.
Oh, okay.
Now, I'll just check to make sure that whatever I typed in on the 27th, actually, well, I can check that right now. I think I re-uploaded it.
Okay.
Yes, I did.
Yeah, because
Okay. Yeah, what I will do generally is I will have one document per section. Okay. But yeah, good to point that out because what I should have done was still put a link in here. Yeah. Okay.
But are we going to get the hints?
Yes, I will put up a hints. Yeah. Okay. I just need to. It's from 2 years ago, so you need to look at them. Yeah. Okay. Actually, I didn't have hints for homework 1, but I'm probably not necessary. So. Okay. All right, glad I remembered that. I saw that when I opened it real quick. It's actually talking about this problem. So, okay. Now, the other property of unit lower triangular matrices that will help is the a unit lower triangular. Oh, okay, so the inverse of a non-singular. So non-singular means the same as invertible. Okay. Unit lower triangular matrix is unit lower triangular. So if a triangular matrix is invertible, the inverse will have the same triangularity. I should mention a unit lower triangular matrix is always non-singular because a triangular matrix is invertible or non-singular if and only if all the diagonal entries are non-zero. Well, if it's a unit lower triangular matrix, all the diagonal entries are 1. So that inverse is guaranteed to exist in that case. All right. All right. So these properties will help us. Now, so taking advantage of a first property, okay. Dang it. Okay. So what happens? Well, okay. Yeah. What happens when we apply multiple elementary row matrices to A? So the idea is, okay. So I'm going to define Eij be the elementary row matrix that subtracts Mij times row j from row I, where I is greater than j, and Mij is given by Aij over Ajj. This is a multiplier from Gaussian elimination. Okay. Then we have the following. So I start with A, and what is the first row operation that the algorithm for Gaussian elimination performs? This operation, E21, is trying to eliminate the 2-1 entry. So it computes the multiplier, M21, multiplies that by row 1, and subtracts it from row 2. So this matrix product has just been carried out. Okay. Then what? We work on the 3-1 entry. So we multiply, so we take this, the result of what we just did, multiply that on the left by the next row operation, E31. And then we keep going, 4, 1, etc., all the way down to En1. So however many rows we have, n rows, right, there should be some dots in between. Okay, there we are, dot, dot, dot. So what this has accomplished here is zeroed out all the subdiagonal entries in the first column. So E21, 31, 41, all the way down to N1. Then what? We go to the second column and do E32. And then we keep going all the way down to the bottom of that column. So this just continues until we get to the very last column that we work on, and the very last row in that column. So that's row n, row n, column n, row n in column n minus 1. So the subscripts here indicate all the entries that had to be eliminated. Now, once that has been done, Gaussian elimination is finished, and we've reduced A to upper triangular form, which I'll call U. So in terms of matrix products, this is what happened. This is what we actually computed. We started with A, piled on all these row operations, these elementary row matrices on the left, and this turned out to be the result. Okay. Now, so more concisely, in terms of instead of describing this in terms of individual row operations, what if we take this a column at a time? So I have M1, M2, and so on, all the way to M minus 1. So I describe in terms of these n minus 1 matrices multiplying A, where Mj is the matrix that is the product of elementary row matrices that eliminate subdiagonal entries in column J. So that is, we have a following. Mj is equal to, so we start with, we go in column J, we eliminate the entry right below the diagonal, so in row J plus 1, then J plus 2, and so on. We keep going. Oh, wait, that should be E. So these are the elementary row matrices. Okay. Okay. So by taking all of these that belong to a specific column and multiplying them together, this matrix here encapsulates all of those row operations that worked on that column. So these two are doing the same thing, just expressed again more concisely. We work in the first column, work in the second column, etc., work on the last column. Now, these individual elementary row matrices, we know what they look like. But what about this product? What does it look like? So we know that Eij is the identity matrix I with minus Mij in row I, column J. So in words, that's the full description of this matrix. And that's what we saw here. This is the identity matrix, and I'm trying to eliminate the entry in row 4, column 1. And and that leads to this entry down here. So we know what those individual row operation matrices look like. So what if I take all the elementary row matrices from column 1 and I multiply them together? So what does MJ look like? Well, that would be a huge ordeal to type out. I will describe it in here, but I'll show you here. Right. Not that. Here it is. Okay, so it's kind of a mess, but the idea is it too is a unit lower triangular matrix because all of these elementary row matrices are unit lower triangular, so their product is unit lower triangular. So we have these 1s down the diagonal, 0s above, but the interesting part is right here. So these are all the entries that work on column K, or all the elementary row matrices that work on column K. So the multipliers and negated multipliers appear in column K. So they're all stacked together in one column. So it has a very nice structure to it. So to give a more concrete example, if I take the elementary row matrix from before. All right, so first I'll describe in words here. Okay. It is the identity matrix again with minus MIJ in the IJ position for I equals j plus 1 up to n. So as an example, whoops, I copied the wrong matrix. I want this one. Okay. I hope this will all fit. Okay. So, I need to fix this here. Okay, so what we have here are 3 elementary row matrices. Oh wait, sorry, I have them in the wrong order. I need to, okay. Hold on. Okay, so this is kind of product that would typically occur. We have, this works on the 2-1 entry, this works in the 3-1 entry, this works in the 4-1 entry. So this operation first, then this and this, because we're always multiplying on the left to stack these row operations, or to have an accumulation. So the product of all 3 of these matrices just turned out to be this right here. We don't have to go through carrying out the multiplication. We just take these multipliers and fill them in, and that turns out to be the product. So it's very convenient to have all that there. Now, So the other thing I'll point out while I have this example up here, now that I have this product, what happens if I take the inverse of this product? Now, I just mentioned that the inverse of a unit lower triangular matrix is unit lower triangular. So we know that much, but also the effect on this matrix is very simple. All it does, here are the negated multipliers. When we take the inverse, all it does is flip the sign of those multipliers. Now, why is that of interest to us? Because of what I'm about to do here. Okay. So I'll copy the equation that I had earlier. All right, next I'll go on to a new page. Okay. So from this right here, all of these matrices are unit lower triangular, and we now know what they look like. Each one of these matrices has the multipliers from that column, so multipliers from first column, multipliers from second column, negated, sitting in that column. So, in other words, if I gave you a list of row operations that were performed, you could form these matrices. You could just write down what they were. Now, okay. Okay. Well, dang, she's missing the best part. Okay. I'm going to multiply on the left by the inverses of these. So, to cancel them out. So I end up with A is equal to... So first I multiply on the left by m minus 1. What? Well, I'm going to name it that, yes. Yeah, but first of all, just to show what's going on here. So then, so multiply by that inverse, and then column n minus 2, and so forth, down to 2. Oh, something went wrong here. Dropped a brace. Okay. Okay. All right. So now we have from left to right, M1 inverse, M2 inverse, etc. And we know what these look like also, because all it did was change the sign of those multipliers. But to add a more concise notation, so this would be L1, L2, L up to Ln minus 1, U, where Lj is equal to Mj inverse. and is the identity matrix with the multiplier Mij in the ij position for I greater than j. And that is shown in the book as well. Okay. So it's just this. So identity matrix, take those multipliers without the minus sign, and just fill them in. Okay. Okay. Now, what happens when we multiply all of the Lj? Because when we took these elementary row matrices that each had one multiplier sitting below the diagonal, multiplied those, that worked out nicely. They just stacked on top of each other. Well, if you multiply all of these, so matrix that worked in the first column, matrix worked in the second column, etc., multiply all those together, that works out nicely too. And thankfully, you don't have to type that out either. So taking all of these and multiplying them together gives you just this. So it's the identity matrix with all the multipliers carried out during the entire Gaussian elimination process that are featured below the diagonal. So we obtain matrix L, which is the product of all of these. Where L is the identity matrix with Mij in the ij position for I greater than j. So in other words, the entire lower triangle is filled with the multipliers that were used or were needed during Gaussian elimination. So we have A equals LU, which is the LU decomposition or LU factorization of A. Okay. And I think that deserves some emphasis. Okay. Bless you. Okay. Now, so in other words, this is what Gaussian elimination implicitly accomplishes. So you go ahead, we're still forgetting about B. We carry out all the required row operations on A. Now, just the straightforward ones, like subtracting a multiple of one row from another. We're not scaling any rows, we're not interchanging any rows, at least not yet. So, from doing all that, we actually have generated all the information needed to get these two factors. U is the row echelon form. That is the output, the results of Gaussian elimination. L is just a matrix that has all the multipliers that we computed during the algorithm. So in other words, okay, so what we can do, so to efficiently obtain this factorization, all we have to do is store each multiplier that we, so as we use it to carry out the elimination, we just store it in the, because what we're doing is we're wiping out all these entries that are below the diagonal. We're creating empty space. So in that space, let's just stuff a multiplier. So in other words, Gaussian elimination on the matrix A, the output will be one matrix where the upper triangle, including a diagonal, has a row echelon form. So it has U. And then the below subdiagonal part has the interesting part of L. And I say interesting part because We know the diagonal of L is 1, so we don't have to store that. And, of course, what's above it is 0. So that is, we can store the interesting part of both L and U within A. So in other words, A is being overwritten by the contents, with interesting contents of L and U. Okay. Now, so how this is helpful to us when solving a system. So then, when we are given a B, we can perform all the same row operations on B by looking up multipliers from L. So in other words, because what I was saying at the outset was we needed some sort of record of all the row operations that had to be performed on A to reduce it to upper triangular form. Now we have that record very concisely. It's just sitting in the lower triangle. Okay. So there's no need to perform this elimination on both A and B, the two pieces of the augmented matrix, contemporaneously. We can just do it on A, store the information in a nice, efficient way, and then have it later when we do have a B. Okay. So now I can describe in a different way in terms of the LU factorization. So AX equals B means that LU X is equal to B. So now I'm going to make a definition here. So let Y equal to U times X. Then we have L Y is equal to B, just by substitution. Okay. So, whoops. So here's how we proceed. Alright, so form Gaussian elimination on just A. So that's A equals to LU. So that effectively computes the LU decomposition. And that takes 2/3 n cubed floating point operations. And then we solve this system. L y is equal to b using forward substitution. So that takes n squared minus n operations. It's a lot less. Now, I should mention this implicitly applies for row operations previously performed on A to B. Now, another way of seeing this is because look what happened here. These are all row operations performed, but this right here, that is the same as, okay, L inverse A. Okay. Now, if we look at the Gaussian elimination algorithm, okay, notice what we have here, that this step right here, where row operations are being performed on B. If I take a look at this step right here, and I compare it to a forward substitution algorithm, which is, where is that? Here. It's basically the same step, only with different notation. Because actually yi equals bi. And Lij, the ij entry, I already told you, that's the multiplier, Mij. So you compare this to that same step of Gaussian elimination, you'll see it's exactly the same thing. So what's happening, so in other words, this step in Gaussian elimination, which we no longer included in an algorithm, this step right here, that is forward substitution to solve a system Ly is equal to B. So all I've done is just taking this out of here, moving it into a separate algorithm so that it can be performed again and again on whichever right-hand sides you have. It doesn't have to be lumped in with this process applied to A. Okay, so like I said, it implicitly applies these row operations to B. Okay, so compare bi equals bi minus mij bj step from Gaussian elimination to yi equals yi minus Lij yj step of forward substitution. It really is the same thing. And finally, I mentioned ux equals y. So we solve. Now we have y. So we have ux equals y using back substitution to obtain the solution x. And that takes n squared flops. And that's it. That's the whole algorithm. And then if I need to solve this kind of system again, where A is the same but B has changed, I don't have to perform this step again. I can just retain the L and U factors that I computed before and use them here. So now repeating with another right-hand side will cost only order n squared flops as opposed to order n cubed flops for solving a system from scratch. Okay. And that's it. So now we have this more efficient way to handle this situation. So do LU once, keep the factors for whenever you need them. Okay, I know time is up, but there's plenty left in this section to continue with next week. Alrighty.